In the previous lesson, I gave an algorithm for the knapsack problem, and we proved that this algorithm actually returns a valid solution, so a subset of size of weight at most W, and that the approximation ratio of our algorithm is 1 minus epsilon. To finish the proof that this is a p-TAS, we now need to analyze the running time. And we need to prove that the running time is polynomial in n, the number of items. So here's our algorithm again. Let's first have a look at step 1. Okay, in step 1, we compute new values, value star, for all of our items. And if you look at how we do that, it's quite simple to analyze. In part 1 of this step, we simply spend constant time to compute the lower bound and to compute delta. And then in step 2, for every item, we can compute its new value, value star, in constant time. So in total, this takes O of n time. Then step 3 is also very easy to analyze, because there we just take the subset that we computed in step 2 and report it. Okay, and reporting, well, we have at most n items, so again, this is at most O of n. So the interesting part of the analysis is to analyze step 2, where we apply our optimal algorithm for integer values to the set x star. So let's have a look at this step. And remember that our optimal algorithm for integer values, based on dynamic programming, had the running time which was n, the number of items, times the total value of all these items. So we're interested in what is the total value of all the items in x star, because that's the set we put into the algorithm. Okay, remember that x star had value star, which was defined as the value divided by delta, rounded up with, well, the value of delta, which is epsilon divided by n times lower bound, and lower bound is the maximum value of any of our items. Now, let's see if we can bound the total value of our items in x star. This is simply equal to the sum over all the items of value star. Okay, so now instead of taking the sum over all the items of their real value star, I'm simply going to say that this is bounded by n, the number of items, times the maximum value star that any such item can have. Okay, so now we're interested in the maximum value star of any of our items. Okay, so let's have a look at that. And there we can use that value star is equal to value divided by delta rounded up. Okay, so that's what you see here. And then, well, the first trivial observation that we can make is that instead of rounding after taking the maximum, this is bounded by, well, rounding the maximum. Okay, so now we're almost there. We just need to plug in the value of delta. So let's see what happens when we do that. Okay, so what's the value of delta? Well, we know what delta is. So let's plug it in, and what we get is the maximum over all, well, the values divided by epsilon divided by n times the lower bound. Okay, and a little bit of rewriting involving what the lower bound is gives us now what we want, right? The lower bound is equal to the maximum value, so this nicely cancels out. So what we get in total is n squared divided by epsilon. Okay, so what do we have in step 2? Well, in step 2, the running time is, as we just analyzed, but in step 1 and 3, it was O of n. So for step 2, we saw that the running time was n times the total value, and the total value was n squared divided by epsilon. So in total, step 2 is going to run in n cubed divided by epsilon. Okay, so the whole running time will be dominated by step 2, and in particular, it will be n cubed divided by epsilon. And as we can see, the running time is indeed polynomial in n cubed, times 1 over epsilon, so it's also polynomial in 1 over epsilon. So it's not only that it's a pitas, but actually it's an f pitas. Okay, so this is nice. What we did was for the knapsack problem, which was NP hard, we developed a pitas. And the technique we used is actually much more broadly applicable. So this was the last lesson of the series of lessons on polynomial time approximation schemes, on pitases. So let's have a short summary after stating the theorem that we proved in this particular lesson. Namely, that for the knapsack problem, there exists an f pitas, which runs in n cubed divided by epsilon time. So now let's see what is the summary of what we did that I promised you. So first of all, in this whole series of lessons, what we saw was, well, a pitas is an algorithm with two parameters. First of all, the problem instance. Secondly, a parameter epsilon that determines the approximation ratio. And that means for a maximization problem, the value that you compute will be at least 1 minus epsilon times opt. And when you would be dealing with a minimization problem, then the value of the solution that you compute should be at most 1 plus epsilon times opt. Okay, the running time of a pitas should be polynomial in the input size n. And for an f pitas, it should also be polynomial in 1 over epsilon. Okay? And what we also saw is a general strategy to design a pitas. It doesn't work for all problems, but it's not only the knapsack problem where it works, but it's actually a number of other problems as well. So what is the general strategy? Well, first you want to somehow develop an algorithm which gives an exact solution, so an optimal solution, for the special case where the values, whatever that means in your particular problem that you're looking at, where these input values are integers. Okay, and often dynamic programming can help you to develop such an algorithm. The running time of this algorithm is typically going to depend on the size of these integers. If you have a problem where the input instance, where the integers are very large, then it's going to be slow and not even polynomial. But if the input integers are relatively small, then the algorithm will be fast. So that's step one. After you do this, you then, if you want to look at the general problem, what you do is you take the input values, which are maybe not necessarily integers, and somehow come up with a way to round these values to integer values. So to replace them by integers. Okay, and for the knapsack problem, we did exactly this, where we replaced this value by value star. And there's also a general way of trying to do this by working with this delta, as you've seen in one of the previous lessons. And then there's a nice way to derive what a good value of delta is. So that's what we did on polynomial time approximation schemes. And well, I hope you enjoyed this MOOC. Thank you.